All right, this is section 4.5, video number 2. And scrolling through these, I have definitely decided I am not going to do all of these. I can post some answers, and then you can use some of these as practice, but I am going to run through a good bit more of them, but just not all of them. Okay, so we are on to number 6. And again, the difference here is with our U substitutions, we are going to have bounds now. So this is a definite integral, meaning we're not going to have a plus c anymore. We're going to get an answer out of this thing. So it's the same general process to start with. You're going to let your u be the composited piece, which is 2x plus 1. Okay, our du over dx is going to be 2. Got to solve for dx, so we'll multiply both sides by dx and then divide by 2 to get our new dx value. So, and this is important, now when I write the integral, I'm just writing the integral. Notice I'm not putting any bounds on there yet. I'm going to do my substitution, so I'm going to get the square root of u times my new dx, which is du over 2. I'll pull the 1/2 out to the front, change u to be u to the 1/2 du, and now I can take an antiderivative. So my antiderivative is going to be u to the 3/2 times 2/3, and I'm not going to put a plus c. I'm going to put an evaluation bar because I do need to evaluate this, but I can't evaluate it the way it stands right now. First of all, I didn't write any bounds in there, but I can't use the bounds 0 and 4 because those bounds are bounds in terms of x. Our variable is currently in terms of u. So I do need to change it back, and that's what we were doing before. So I'm going to simplify. So 1/2 times 2/3 is 1/3. And now I'm going to put my original u value, which is 2x plus 1 raised to the 3/2 power. Now I can evaluate it from 0 to 4. There's actually a second method, which we will learn later in this video. But for right now, this is fine. So now I can just perform fundamental theorem of calculus part 2. I'll plug in the upper bound. Let's see, plugging in a 4 is going to give me 2 times 4 plus 1 is 9. So 9 to the 3/2 power minus 1/3. Plugging in 0 is going to give me 0 plus 1, so that's 1 to the 3/2 power. Okay, both of these are things that we can do without a calculator. So I'm going to have 1/3. So 9 to the 3/2. 9 to the 3/2 literally means 9 cubed and then take the square root. If you don't know what 9 cubed is, that's okay. I don't really know it off the top of my head either. But I can do the square root part first. I can do the square root of 9, which is 3, and then cube that, which is 27. That makes it much easier to deal with. Now, 1 to anything is 1. So I'm going to get 1 to the 3/2, which is 1. So 1 times 1/3 is 1/3. So really what we're going to get here is 27/3 minus 1/3, or 26/3. And that is the definite integral. Okay? Number 7, same general idea. I have a definite integral. My composited piece is the denominator, but the more composited piece is the 3 minus 5x, which is within the denominator because that's all being squared. So I'm going to let u be 3 minus 5x. The du over dx is going to be -5, solving for dx. And you will get used to this process after you do it enough. So then we can go ahead and replace the stuff in our integral. So I don't like the dx being on top. That tends to confuse people. Although they'll always put the dx on top, it seems like, when there's really a 1. So I'm just going to put the 1 up there. I'm going to bring the, well, normally I would bring the dx off to the side, but bring the dx off to the side and just know that you really have a 1 up there. So I'm going to replace the 3 minus 5x with a u, so that'll be u squared in the denominator. My new dx is going to be du over -5. So let's bring the -1/5 out to the front. I want to have that not as 1 over u squared, but bring that up to the top, so that would be u to the negative 2 du. Okay, we'll take our antiderivative now. So we're going to get negative 1/5. Antiderivative of u to the negative 2 is u to the negative 1 divided by negative 1, which is multiplying by the reciprocal of negative 1, so it's still just negative. Okay, I can multiply those two negatives together, and I can change, if I want to, the u to the negative 1 back to, oops, forgot my bar, 1 over u. So I'm going to have 1/5 times 1 over u, but I want to change the 1 over u to 1 over 3 minus 5x. Now we can evaluate that from 1 to 2. So let's see what we're going to get here. We're going to get 1/5. If I plug in a 2, I'm going to get 1 over 3 minus 10, so that's negative 7, minus, if I was to plug in the 1, I'm going to get 1/5, and then times 1 over 3 minus 5, so 1 over negative 2. So it looks like it'll be easier to factor the 1/5 out, although you don't have to. And then I'm going to get negative 1/7 minus 1/2. So in order to simplify this, I'm going to have to get a common denominator. It looks like it'll be 14ths, so minus 2/14. That minus minus becomes a plus 7/14. I think I'm doing this right. Looks right so far. So 1/5, negative 2/14 plus 7/14 is 5/14. That actually works out pretty nicely because 1/5 times 5/14, the 5s are going to go away. We get 1/14. So a bit messy with all the fractions and the minuses and all that kind of stuff there, but that is the answer. So you just have to be really careful. All right. Okay, this next page is just a bunch of more practice. So what I'm going to do is I'm going to give you the answers and then let you guys at some point in time use these as practice. So the first one, if you do everything correctly, should give you 1/4 x squared minus 1 to the 4th power plus c. Number 9 is going to end up giving us sine of 6x plus c. Number 10 is going to be 1 over 32 times 4x squared plus 3 to the 4th plus c. And then number 11 is going to end up being negative 2/3 cotangent of x to the 3/2 power plus c. So again, use those as practice. See if you can match the answers. I think that would be a good idea. All right, so we're going to move on. Now it says examples continue, too much stuff. Too much stuff mostly because of number 1, but you can never have too many of these examples to practice because it is definitely the best way to learn. All right, so in number 1, the composited piece is pretty obviously 2x plus 1. So du over dx is going to be 2. So 2 dx is du. Solving for dx, we get du over 2. Substituting in for my integral, we are going to get x times the square root of u times the new dx, which is du over 2. And you should see that we're going to end up with one of those things where we have an issue again. I can pull the 1/2 to the front, but this x is going to be a problem. and I'll rewrite the u to the 1/2 power. So we have to find a way to get rid of that x. It needs to be in terms of u. Once again, I have an equation that has x's and u's in it, so I can use that equation to try and manipulate this. So, using that equation, I can subtract 1 on both sides, so we get u minus 1 equals 2x. Solving for x, because that's what I need to get rid of, is going to be u minus 1 over 2. So that's what I'm going to plug in for my x value. 1/2 the integral u minus 1 over 2 times u to the 1/2 du. Personally, I would prefer to get rid of that fraction on the inside of the integral, so I'll pull another 1/2 out to the front and multiply it by the original 1/2 and get 1/4. The integral of u minus 1 times u to the 1/2 du. Now I can distribute the u to the 1/2 into everything, and we're going to get the integral of, let's see, that'll become u to the 3/2 power minus u to the 1/2 power du. And now we can take antiderivatives. So we're going to get 1/4 antiderivative u to the 3/2 is going to be u to the 5/2. Dividing by 5/2 is multiplying by 2/5. Minus u to the 1/2 becomes u to the 3/2. Dividing by 3/2 is multiplying by 2/3 plus c. So last thing is I'll distribute the 1/4 and replace the u value with 2x plus 1. So 1/4 times 2/5 is going to be 1/10. U was 2x plus 1. Don't forget the power is 5/2. Minus 1/4 times 2/3 is going to be 1/6. Replace the u with 2x plus 1. It is now to the 3/2 and plus c. So again, just know that you can do some of that algebra if you have to manipulate some of these formulas. Okay, number 2 is relatively the same type of problem where you're going to have to do a little manipulation. It's not as difficult, so I'm just going to give you the answer. And again, I think it's good if you take some time to practice it. This one should end up being 2/5 x plus 2 to the 5/2 minus 4/3 x plus 2 to the 3/2 plus c. So again, go ahead and practice that one at your own time. All right, let's move on to the next page. All right, so I said that there was a second way to do a definite integral. It's what's called the change of variable for the definite integral. It says that if the function u equals g of x has a continuous derivative on a to b and f is continuous, then your integral is what it is there. So I'm not going to write that specific part out right there, but the important thing is if there's another way to do this problem. Now this first one, probably not the best example to start with, but at least it'll give us an idea of what I'm talking about, because of the fact that I could literally just multiply the x into the x squared plus 1, and then we could just do a straight power rule, but we're not going to do that. We're going to show that the composited piece x squared plus 1 is our u value. So we're going to let u be x squared plus 1. The derivative then is 2x, so multiplying the dx over, and then solving for dx, it'll be du over 2x. Okay. I could do this the original way. I could still write my integral, write an x, this will become u. My new dx is going to be du over 2x. The x's will cancel out, and I can pull the 1/2 out to the front, and then I've got u du to take the antiderivative of. Okay, I could take the, I may as well just finish it. I can take the antiderivative, which is going to be u to the second power divided by 2 is multiplying by a half. And then we'll put our evaluation bar, which is going to be 1/4, replace the u with x squared plus 1, and then evaluate it from 0 to 1. Okay, I'll do that part in a second. There's a second way to do this, and you will have to know how to do both of them. The second way is, maybe I don't want to do this step. Maybe I don't want to change everything back into x. I don't have to. Okay, everything else up to that point is pretty much going to be the same. I'm going to end up with, let's use orange. I'm going to end up with the integral of x times u du over 2x. All that's the same. But I'm going to change these bounds of integration. I'm going to change them into terms of u so that I no longer have to worry about changing back at the end. Well, the idea is that these are x values. If I were to plug 0 into x squared right here, I'm going to get 0 plus 1, and that is a new u value. So if I plug 0 and I get 1, so my new lower bound in terms of u is 1. If I take the 1 and I plug it in, I'm going to get 1 squared, which is 1, plus 1 more is 2. So my new upper bound is 2. Now, when I get rid of the x's, everything in that integral is in terms of u. So I can do a straight evaluation from here. So now I can just do the integral from 1 to 2 of u du. Okay, and that's going to be 1/2 u squared from 1 to 2. So if I plug in 2, I'm going to get 1/2 of 4, minus if I plug in 1, I'm going to get 1/2 of 1. So that's going to be 4/2 minus 1/2, which is 3/2. Now let's go ahead and show that the green one up at the top would have given us the same thing. If I plug the 1 in, I'm going to get 1/4 of 1 plus 1 is 2. If I plug 0 in, I'm going to get 1/4 of 0 plus 1, which is 1. So once again, okay, something didn't work out there. Oh, I see it. Jeez. You guys probably caught this before I did. I forgot my squared right there. That makes a big difference. So that squared and that squared won't change the 1 part, but certainly does change the 4 part. So 2 squared is 4 minus the 1. So it's still going to give me, in this case, 3/4. Wait a minute. That means I messed up on the orange one. Oh, I did mess up on the orange one. Man, I'm just making all kinds of mistakes here. Hopefully you guys are catching my mistakes. I forgot to bring the 1/2 out to the front here, which gives me another 1/2, which makes that 1/4 as a denominator. All right, hopefully you guys caught those mistakes before I did, because then that makes that 3/4. Yeah, now they're both right. Geez. Okay, but anyway, this is the change of bounds right there on that example. And you will have to be able to do the changing of the bounds. All right, we are going to skip all the way down to number 7. Completely skip a whole page there. The rest of them are good practice for you guys. Number 7 has something interesting in it that we'll do. So once again, you should be able to see that the most composited piece there is the x cubed plus 3x. So we'll let u be x cubed plus 3x. So du, by the way, I'm going to start skipping one step. I'm not going to write du over dx. I'm going to write the du as the derivative and then times the dx. That's usually the way it's done. So that'll be 3x squared plus 3 dx. So I'm just kind of skipping that du over dx and multiplying the dx to the right. Just makes it one less step that I can solve for dx. So it'll be du over 3x squared plus 3. So now let's go ahead and take our integral. So that's going to become u to the 4th times x squared plus 1 times my new dx, which is du over 3x squared plus 3. And you might initially look at that and say, wait a minute, those are not the same thing. That's not going to cancel out. It will actually cancel out because I can factor a 3 out of that denominator and bring that out to the front. So that'll be 1/3 of the integral of u to the 4th x squared plus 1 times, now it's going to be du over factoring that 3 out, x squared plus 1. So again, sometimes you have to do a little extra algebra to simplify these things. So I'm going to get the integral of 1/3 u to the 4th du, and you should agree that that makes it much, much easier at this point. So that'll be 1/3, so 3. U to the 4th is going to become u to the 5th times a 5th plus c. So that'll become 1/15. Replace the u with x cubed plus 3x to the 5th power plus c. Okay, mostly because of the factoring on that one, I found that one to be an interesting problem that I thought we should work on. Number 9 is a bit tricky, so we're going to skip down to number 9. And I'm only going to do one more after that, so I realize the video is running a bit long, but we're going to do it in 2 videos as opposed to breaking this into 3. So the problem with number 9 is tangent squared x and secant squared x are both really the same kind of composited things. Both of them are squareds. So I could pick tangent or secant as the interior function. What you want to do here is you want to pick the appropriate u so that when you take the derivative, it gives you the other function. So for example, I'll pick the wrong one first. If I pick secant of x, I'm going to erase this, so don't write this in because this is not right. The derivative would be secant of x, tangent of x. Well, when I let u be secant of x, that there would become u squared. But that secant of x, tangent of x is only going to get rid of one of these tangents right here, and it's still going to leave me with a secant and a tangent as a quotient actually. So this is wrong. So that's not going to work. But what I can do is I can let u be tangent of x, because we should remember that the derivative of tangent is secant squared x dx. So dx then is going to be du over secant squared x. So my integral will become, oops, not tangent squared, that's u squared, times secant squared x times my new dx, which is du over secant squared x. The secant squareds are going to go away, and that leaves me with the integral of u squared du. Much simpler antiderivative to take. That will become 1/3 u cubed plus c, but then we'll replace u with tangent of x, so we're going to get 1/3 tangent cubed x plus c. All right, so that one you might have to do a little bit of thinking on in order to get to the right answer. All right, last one that we're going to do is number 11. So let's go down to that one. So we've got cosine cubed x plus 1 times sine of x. That's our integrand, and it's a definite integral. Okay, I am probably going to change my bounds on this one, although you don't have to. When it doesn't say which method to use, you can use either one that you want to. I usually choose to change my bounds when I can, because to me it makes it easier. I don't have to remember to turn things back into x later. So again, you might want to ask yourself, what is the most composited piece? Well, it might look initially like it's cosine cubed x plus 1. But technically, the cosine cubed x is a composite within a composite. So it's really the most composited piece. And if you tried to use cosine cubed x, you're going to end up with a derivative 3 cosine squared times the derivative of cosine, which is negative sine. You're still going to have cosines left over, even though you're trying to get rid of that sine of x from the outside. So the u value has to be just cosine of x, which makes our derivative negative sine of x dx. So dx is du over negative sine of x. And if all that stuff that I said went a little bit too fast, go back, watch it again, think about it, and watch how it's going to work out here. So my new integral will be the integral of replacing cosine with u, so that'll become u cubed plus 1, can't lose the 1, times sine of x times the new dx, which is du over negative sine of x. Now this is the way that you would leave it if you were going to change the bounds back at the end. I am going to change the bounds now. So if I were to take 0, plug it in for x, cosine of 0 is 1. That's my new lower bound. If I was to take pi thirds and plug it in for x, cosine of pi thirds is a half, so that's my new upper bound. Okay, I'm going to use a couple more properties here. First of all, we did not get rid of that negative. It needs to go out to the front. So I'm going to have the negative integral from 1 to 1/2 of u cubed plus 1 du. And the antiderivative of u cubed plus 1 is not terribly difficult. I don't like the fact that in this case the bounds are upside down. It's going from 1 to 1/2. But remember, if you flip the bounds, then you make the whole thing negative. Well, the whole thing already is negative, so I'm just going to make it positive. So now my bounds will go from 1/2 to 1. The negative out front now becomes a positive, and I've got u cubed plus 1 du. So then my antiderivative is going to be 1/4 u to the 4th plus u, and we'll evaluate that from 1/2 to 1. All right, let's see what we get. If we plug in 1, we're going to get 1/4 plus 1 minus, if we plug in a half, so let's see, a half to the 4th power is a half times a half times a half times a half, so that's going to be a 4th, an 1/8, a 16th. So 1/4 times a 16th is 1 over 64 plus 1/2. Now we just get to try and combine all this stuff. So we can put everything in terms of 64ths. So 4 goes into 64 16 times. So it'll be 16 over 64 plus 64 over 64 minus 1 over 64 plus 32 over 64. So let's see, 16 plus 64 is 80, minus 1 is 79, minus 32 more is 79 minus 32 is going to be 47, so we should get 47/64. And that's the answer. All right, the rest of these I am going to leave as practice for you guys. This video has gone on way too long, but that is the end of the lesson.